Okay, so let us compare these quantities. Okay, so you can see that inertia. So in linear motion, how will you calculate the inertia? That is only mass. What is the mass of the body that will represent the inertia of the system? Then in case of angular motion, okay, to represent the inertia, there is one term which is nothing but mass moment of inertia, I, and it is calculated as equal to mk square, mk square. Okay. Then next is your displacement. So in case of linear motion, displacement is linear displacement, x, unit is mm. But in case of angular motion, displacement is in terms of angle, angular displacement. We denote it by theta, okay, and it is measured in radian. Velocity unit is mm per second in linear motion, and in case of angular motion, we use the angular velocity omega, radian per second. Similarly, for acceleration, linear acceleration mm per second square, angular acceleration alpha, radian per second square. Driving agent means what is causing the motion. In case of linear motion, it is the force which is causing the motion, and in case of angular motion, what is behind the angular motion? That is nothing but torque. If some torque is acting on the object, then it rotates, it turns. Okay, and torque, it is given by force into radius. Radius you measure from the axis of rotation. Then kinetic energy. So in case of linear motion, it is 1 half mv square. In case of angular motion, it is 1 half I omega square. Okay. Then work done is F into X. How you calculate the work done? What force is acting and object has displaced by how much distance. So multiplication of these two will give you work done. In angular motion, how you will calculate the work done? Okay, in place of force, you will use the torque here, and in place of your linear displacement x, you will use the angular displacement theta. So these parameters get changed in angular motion. You have to consider the corresponding parameter. Okay, uh, getting this.
Yes, sir.
Okay, you note down here the formula for kinetic energy for linear motion, and it is for angular motion. Okay. Okay, so now let us discuss this methods of solving the kinetics problems. So two methods are there which you might have studied in first year also. Okay, so first is your D'Alembert's principle, and second is work energy principle. So what is D'Alembert's principle? Okay, what it says, suppose there is one mass. Okay, mass could be anything. It could be your car, bike, any object which is moving, and say it is having acceleration. Okay, this mass is having acceleration in this particular direction. Say this particular direction is, say this direction is direction y. Okay, so what it says, as it is under unbalanced forces. Okay, there might be some resultant force in y direction. Because of that, this object is in motion. Okay, and as it is having some acceleration, means you can say that the motion is not uniform, its velocity is changing. Having acceleration means what? The velocity is changing, either increasing or decreasing. Okay, so some force might be acting behind that. Okay, so what D'Alembert's principle says, that if you add, okay, it is your active force is which is causing the motion. There is some resultant force in y direction. Because of that, the body is undergoing acceleration. Okay, so this resultant force, and you if you add an imaginary force which is equal to mass mass into acceleration in that particular direction. So it is acceleration in y direction. Okay, in opposite direction of the active force means minus. Okay, then the body can be considered under dynamic equilibrium. Okay, that is summation of these forces, active forces, and the inertia force, it is called as inertia force, m into ay, will be equal to 0. Okay, now with the help of equation of statics, you will be able to solve this equation. That you have, it is an equation of equilibrium, right? Though there is no equilibrium, but with the help of D'Alembert's principle, by adding this imaginary force, okay, in opposite direction, you have brought it to dynamic equilibrium, and now it can be solved. Is my voice clear?
Yes, sir.
Okay.
Yes, sir.
Okay, so do you understand this D'Alembert's principle?
Yes, sir. Yes.
Okay, so I have applied the D'Alembert's principle in particular direction. Why? Okay, suppose if I want to apply the D'Alembert's principle in x direction, then I have to see what force is, what is the resultant force in x direction, fx equal to mass into what is the acceleration in x direction. Okay, this acceleration in y direction will not be applicable here. So it is direction specific. Okay, means in D'Alembert's principle, vector quantities are involved. Vector quantities are involved. Okay. Now there is the second method, that is work energy principle, and you will find this work energy principle easier than D'Alembert's principle. Okay, because in this work energy principle, vector quantities are not involved. Okay, you can do the sums using the scalar quantities. Okay, so we will see that also, what is work energy principle. Okay, so see work, what it says, it has two terms, work and energy. Okay, so if a body, say here there is mass, okay, say it is position 1 of the mass, and then it goes to position 2. Okay, so what it says, then when it travels, when it moves from position 1 to position 2, okay, and if there is change in kinetic energy, okay, there is change in kinetic energy, Okay, for example, say here there is some initial velocity u, and at point 2 there is final velocity. Say that velocity is v. Say velocity has changed. Say it has uh, increased or decreased depending on condition. Okay, so whatever change is there in kinetic energy, that change will be equal to the work done by the forces. Work done by the forces. Okay, some force might have acted, right? Some force might have acted at this point, because of that the body got sudden acceleration, its speed got increased. Okay, or some negative force, some force might have acted in this direction, because of that body is moving in this direction, force is acting in the opposite direction, because of that what will happen, the speed will reduce. So you will find that velocity is less than the initial velocity. There will be change in kinetic energy. Okay, so that change in kinetic energy will be equal to what is the work done by this opposing force. Okay, so work done, you know how we calculate the work done. Work done we calculate with the help of force into distance, F into x. Okay, in case of linear motion, in case of linear motion. But in case of angular motion, you have to take the corresponding parameters. So force will be replaced by torque, you know, and linear distance, linear displacement will be replaced by angular displacement, theta, t into theta. Okay, okay. So in case of angular motion, this will be the formula for us. Okay. So by this particular equation, you can solve the problems of kinetics. You can see that in this particular equation what is unknown, and that unknown can be found. Okay, understood it?
Yes, sir.
Okay, so work energy principle is comparatively easier than the D'Alembert's principle. Okay, and in next lecture we will be solving one or two numericals on the basis of work energy principle. These problems which we are going to solve are often repeated in university examinations. Okay, so it will be wise to attend the next lecture also. For today, we'll stop here. Any doubt or anything you want to ask me as a class teacher or as a subject teacher?
No, no.
Okay, so we'll stop here. Okay, example is there. I am ending the meeting now.
Okay. Thank you, sir.